Welcome to episode 56 of the Pulse of Physiology. I'm your host, Dr. Jim Davis, and today we're covering ventilation perfusion matching. This is the process that ensures an optimal balance between airflow, which is ventilation, and blood flow, which is perfusion, specifically in the lungs. By the end of this episode, you'll understand how ventilation perfusion coupling works, how local changes in oxygen and carbon dioxide levels regulate pulmonary blood flow and bronchial diameter, and the impact of VQ mismatches like shunt and dead space. So let's get started. So ventilation, as I mentioned earlier, refers to the amount of airflow into and out of the alveoli, while perfusion refers to the amount of blood flow through pulmonary capillaries. The ideal VQ ratio is 1:1, meaning ventilation and perfusion are perfectly matched. However, ventilation perfusion matching varies throughout the lung due to gravity, postural, and regional differences in blood flow and ventilation. To maintain efficient gas exchange, local mechanisms adjust blood flow and airflow in responses to oxygen and carbon dioxide levels. Low alveolar oxygen results in pulmonary vasoconstriction. We are reducing blood flow to poorly ventilated areas and redirecting it to better ventilated regions. High alveolar carbon dioxide results in bronchodilation, and this increases airflow to remove excess carbon dioxide more effectively. And then finally, we have low alveolar carbon dioxide. This results in bronchoconstriction, which reduces airflow to conserve carbon dioxide to help us maintain pH. Now, these adjustments ensure that blood flows where oxygen levels are highest, and airflow is directed where CO2 removal is needed most. Now, when ventilation and perfusion are not well matched, gas exchange efficiency decreases, and so there are two main types of VQ mismatches. Shunt, which has a low VQ ratio. A shunt occurs when blood is perfusing alveoli that are not ventilated, meaning no fresh oxygen is entering the alveolus. This can be caused by airway obstruction, collapsed alveoli, which has a cool name for it, atelectasis, or fluid-filled alveoli, such as what happens during pneumonia. Blood leaving the lungs remains poorly oxygenated, leading to hypoxemia. Then you've got dead space, so this is a high VQ ratio. Dead space occurs when alveoli are ventilated but not perfused, meaning no blood is available to pick up oxygen. Pulmonary embolism can be a cause, and this is when there's blocked blood flow to alveoli or localized vasoconstriction. Alveolar air remains similar to atmospheric air, and oxygen transfer is reduced. So gas exchange efficiency depends on partial pressure differences. As we've mentioned previously, alveolar pressure of oxygen is about 104, arterial oxygen is about 100, alveolar carbon dioxide is about 40, as is arterial carbon dioxide. These gradients drive oxygen into the blood and CO2 out of the blood. And remember that CO2 goes from the bloodstream into the alveoli because venous carbon dioxide is about 46. Now, VQ mismatches disrupt this balance, and this can lead to oxygenation issues. So to summarize, VQ matching optimizes gas exchange by balancing airflow and blood flow. Low pressure of oxygen causes vasoconstriction to redirect blood to better ventilated areas. High carbon dioxide causes bronchodilation to enhance CO2 removal. Shunts that have a low VQ reduce oxygenation by allowing blood to bypass ventilated alveoli. And dead space, which is a high VQ, reduces gas exchange by sending air to unperfused alveoli. So that's it for episode 56 of the Pulse of Physiology. I hope this episode has clarified how ventilation perfusion matching ensures efficient gas exchange. Join me next time for episode 57, where we'll discuss minute and alveolar ventilation and how they determine effective respiration. Until then, keep questioning, keep exploring, and stay curious.